So this is part 4 of our addition reactions to alkenes. Last time we looked at, and we ended quickly, with the catalytic hydrogenation reaction. This is probably the easiest reaction to remember for alkenes. You're going to be adding hydrogen gas across an alkene. You'll notice we start with carbon-carbon double bond. It's reduced to a carbon-carbon single bond, and we get hydrogens added. This requires the presence of a metal catalyst such as platinum, palladium, or nickel. So another type of reaction, not as easy to remember, is going to be a carbene to an alkene. Uh, Remember, a carbene is one of our four major reactive intermediates other than the radical, the carbocation, and the carbanion. This has a carbon with a lone pair of electrons and two covalent bonds to hydrogen. You'll notice carbon still has one, two, three, four different things attached to it, so it still has a neutral overall charge because of its valence of 4. What we'll have here is a cascading of arrows where our nucleophile and our carbene are going to interact all together. So we can redraw this. Here's our carbon-carbon single bond that began as an alkene. Now we have our carbon from our carbene attached, and we'll get this cyclopropane, which is highly unstable and will react right away in the next step of whatever reaction you use. Simmons and Smith have a reaction named the Simmons-Smith reaction. They use this diiodine zinc complex to form the carbene. I don't think that you'll see this much on the ACS exam, maybe just the actual prediction of the products. The next reaction we'll see of alkenes is called an epoxidation. If you remember towards the beginning of the term, we looked at carbon in a three-membered ring with an oxygen, and that functional group is called an epoxide. This can be formed with an alkene and a peroxy acid. It's kind of like a carboxylic acid with an extra oxygen in there. You'll notice we have one, two, three oxygens. There will be an oxygen-oxygen single bond, which will be our peroxide bond. This will form our epoxide as well as carboxylic acid. Let's take a look at the mechanism. We'll have our alkene, and I've set this up so hopefully that you can see the flow of arrows a little bit easier. We're going to have this nucleophilically react with this oxygen. The oxygen-oxygen peroxide bond is going to break, which will drive the whole process forward. So here's our oxygen-oxygen bond breaking. We'll form a carbon-oxygen double bond, which will overload this carbon, so we'll break this bond, grab this hydrogen, and just the hydrogen onto this oxygen, and then this set of electrons will go back and add to the other carbon. We can look at our transition state. We have our carbon-carbon interaction from our alkene. We still have a single bond there. These will be R groups. Here's our oxygen, oxygen. The peroxide bond is broken. We form a double bond here. We lose this double bond and pick up a hydrogen. So we can piece this together, and you can see the epoxide forming, and you can see how ultimately the peroxy acid formed our carboxylic acid. So spend some time and practice this reaction. So here's two examples of the epoxidations, and the most common reagent that you'll see used is abbreviated MCPBA, which stands for metachloroperoxybenzoic acid, with our structure shown here. It'll undergo that mechanism that we just looked at, and a great solvent for this, a nonpolar solvent, this is methylene chloride, will be used to dissolve everything. Interesting thing about this reaction in the epoxide is we can control it if we know or have the ability to start with geometric isomer. This is the cis alkene. You'll notice in our products the arrangement of the methyl groups are both still pointing in the same direction, or cis. Here's an example with a trans alkene. The methyl groups are in opposite directions. You'll see in the product of our epoxide, the methyl groups are going opposite. So we can get stereochemical control with this if we start with a cis or trans alkene. So why would you want to make an epoxide? Well, here's a great application reaction. This is called an acid catalyzed ring opening, or acid catalyzed epoxide ring opening. Here's our epoxide that we just looked at. We can react this with acid. Of course, acid is going to be in an equilibrium reaction with water, so we will have hydronium. We'll use hydronium in our mechanism. So we're going to protonate our epoxide oxygen from the hydronium. We'll neutralize this and ultimately form water. When we protonate the oxygen, we get a positive charge on it, ultimately driving the electron density towards that. Water will go through a backside attack. Break this covalent bond, and that'll free up that positive charge. We'll get an alcohol. Water will then, once it's attached, as we saw before, have 3 bonds and a lone pair on our oxygen, so a positive charge. Another portion of water can deprotonate, take care of that positive charge. Will regenerate a little bit of acid. Anytime you use acid, you'll form acid in the very last step, and that's what we've seen in attacks with water with the deprotonation step. You'll notice this does have a unique relationship. We have alcohols. They are on opposite ends, and this is an anti-relationship. This has a few different names. It's a diol because we have 2 alcohols. Another functional group name that you may want to be familiar with is if you have alcohols on neighboring carbons, side-by-side carbons, it is called a glycol. So a glycol is going to be a sugar derivative. So this would be our anti-glycol. This type of reaction with our acid catalyzed ring opening of epoxides will be called a dihydroxylation. So from the alkene, we can form an epoxide and ultimately get an anti-relationship of our alcohols. Well, you may be thinking to yourself, if I can do an anti-dihydroxylation, what about a syn? Well, you can, but it does not go through an epoxide. The utility of the epoxide, as we saw, and let's just rewind a second, allows us to have the backside attack of water so that we'll get opposite orientations of our alcohols. Now, a syn dihydroxylation, there's a couple ways we can do this. One is using osmium tetroxide, which is OSO4, and look up some information on this. We want to do this in a glove box. This is really nasty stuff. I wouldn't want to be using it very much. We'll also, in addition to the osmium tetroxide, you'll use hydrogen peroxide, and just the general reaction here, you'll get a syn addition in that the alcohols are going in the same direction. A little bit about the mechanism. We're going to have a lot going on with these electrons. We're going to have the nucleophile come in and attach to this oxygen. We're going to send electrons onto the osmium, and then in turn, this bond will go back to the carbon. So, kind of similar to the epoxide, but it's not going to be a three-membered ring. We get a five-membered ring. So, I've drawn in these red lines where our new bonds are formed. So we have one of the pi bonds is now here. The other pi bond from the osmium to the oxygen is here. And this pi bond is going to be a free lone pair of electrons, which I've also colored in red. The last step, don't worry about the mechanistic steps of it, is going to remove our osmium tetroxide, hydrogen peroxide. This will oxidize back our double bonds, and we will be left with our two alcohols, our diol, or our glycol. So do be familiar with all of those terms, and they will have the syn orientation. Now there's another way this reaction can be performed. This is using potassium permanganate and sodium hydroxide, or a strong base like potassium hydroxide. This will undergo a very similar reaction as the osmium tetroxide. The arrows will be the same, but the permanganate will have a structure that looks like this. Everything else is identical. Now there is an extension of the potassium permanganate reaction. I wrote it out here. You can heat up the solution so you can have a warm, concentrated, or add in acid, and you'll ultimately get oxidative cleavage, where we're going to break apart this carbon-carbon bond, and we'll get an oxidation to occur. This will form ketones, or carbonyl, and depending on what our groups are, so you'll notice here in our starting material or our starting alkene, I have these two black R groups. We're splitting right down this carbon-carbon double bond, and you can think of the glycols or diols ultimately being oxidized to this ketone. Here's our two R groups. On the right side we have an R and a hydrogen. This forms an aldehyde because we have a hydrogen directly attached to a ketone. The aldehyde is very reactive, and in this acidic solution, this will oxidize to a carboxylic acid. So we'll write out carboxylic acid. Now there's another type of oxidative cleavage reaction. This is called ozonolysis using ozone. Ozone has a chemical structure of three oxygens bound together. We can take our same substrate with the two R groups on the left and the red R and the H just to distinguish the two on the right. This will give our ketone, just as we saw with the last oxidative cleavage, and we will get an aldehyde. These conditions are a little bit milder, so we can actually isolate the aldehyde. I'm going to go ahead and stop here with this part, and we'll have another part. Thank you.